Hello, everybody, and welcome to Unit 1, Part 4 of our astronomy course. In this part, we're going to talk all about light, our cosmic messenger, the information resource that we have coming from the universe here to Earth, where we can detect it using telescopes and CCD cameras, CMOS cameras, the kind of thing you carry around in your cell phone. But we can gather up the light that's coming from the universe, and then we can use that information to determine pretty much everything we know about the universe. Because light is our information resource. It is our cosmic messenger. As you can guess, light is probably a pretty important part of astronomy since it is pretty much all the information that we get, our electromagnetic messenger of light. So let's spend a little bit of time getting to know light. And the first thing I really want to impart onto you is that light really is our messenger. Light is how astronomers have pieced together all the information that we have, or nearly all the information that we have about the universe. When we look out at the night sky and we see all the stars out there, we physically can't go there. We barely have a spacecraft that can reach our nearest neighboring planets. We can't go to the nearest neighboring stars. And whenever we look out and see an image like right here, the Andromeda Galaxy, that's 2.5 million light years away, we certainly can't go there. So how do we know so much about the Andromeda Galaxy? How do we know so much about stars and how they work, how they function? How do we know anything about the nature of the universe? Well, almost all of it we can glean from the light that comes to us. Astronomy is a lot more than pretty pictures. Contained in this image, this capture of light from another galaxy, a capture of light from outer space, if we understand the nature of light, then we can start determining amazing things like what is the chemical composition of the stars, what are chemical compositions of cosmic objects, what are their temperatures, what are their other properties. And it's through our knowledge of light that we can do all of that. So understanding what light is, getting acquainted with light, is a very important task and a very, very rewarding one since light carries so much information. So light is our messenger from the universe. It's not our only messenger. We have a couple of other resources that bring us information. So we have light, which is technically electromagnetic radiation, very recently discovered yet predicted from by Einstein, are gravitational waves, another resource of information that we can use to learn about our universe. There are particles that are streaming in from all around the universe, and we can use the particles themselves to learn about the universe, things like cosmic rays. And then there are other particles called neutrinos that we can use to learn stuff about the universe, but the vast majority of everything we know comes from the light. It is where we have the most knowledge, the best detectors, and I've spent most of the time learning about the universe. It is our view of light. So our goal is to really understand the nature of light so then we can leverage all the amazing properties of light, our knowledge of light itself, to gain insights to the very nature of our universe. So light is our messenger. And light is just really fun to think about and really, really fun to play with. Because light, while it seems to be instantaneously fast to us here on Earth, if I shine a light, it seems to turn on instantly, and it seems to have gone all the way across the room and hit the wall almost instantly, except it's not infinitely fast. Light has a speed limit. It has a finite speed. And the weird part is it doesn't matter what kind of light we're going to talk about. All light has that same speed limit, and all light travels at that same speed. It is a constant of the universe. It is a universal speed limit that cannot be exceeded. And it doesn't matter what type of light it is or how you're measuring that light, it's always measured to be traveling at the speed of light. So the speed of light is a number. It gives a speed. So in science, we're going to use meters per second. If you want to know the precise number, it's right here, 299,792,458 meters per second. Notice there's not any uncertainties on that because this is something that we can calculate directly from theory. We now understand that well enough, so you could do a direct calculation from theory of what the number should be. You can confirm this by measurement. If you want to go ahead and round that, you can say 3.0 times 10 to the 8th meters per second. That's 300 million meters per second, or you can say 300,000 kilometers per second are the typical ways that people mention the speed of light. Something a little bit more familiar to you, that's 670.6 million miles per hour. Insanely fast, absolutely absurdly fast. So fast that here on Earth, it feels like light travels instantaneously. However, cosmically, light is tragically slow. And I'm going to try to demonstrate this. And I love just walking through all this, because this is where it gets a little bit mind-blowing. You realize that anytime that you're using a telescope, or really just using your eyes, you're looking at anything, you're looking back in time. When we look at this image of the Andromeda Galaxy, we're not seeing it as it is now, we're seeing it as it was. Its distance is 2.5 million light years away. Remember, a light year is how fast light can travel in 1 year. It has a set speed that all light travels at that same speed. So it's just the distance that it would travel in 1 year, which means the Andromeda Galaxy, being 2.5 million light years away, is taking that light 2.5 million years to reach us on Earth and collect it and make an image of it. So this picture of the Andromeda Galaxy is not the Andromeda Galaxy as it is right now. It is as it was 2.5 million years ago. You are literally looking back into the past. This is the only time machine that we really have, and it only looks into the past. The furthest galaxies that we see that are tens of billions of light years away, you're looking back to just the moments when galaxies were first forming, the earliest parts, the earliest histories of our universe. When you look at the sun, don't stare at the sun, you're seeing the light that left it a little over 8 minutes ago. The sun could blink out right now, and we wouldn't have a clue for 8 minutes, because the light that would be leaving the sun right now, as it blinks out, it would take 8 minutes for it to get to here, to Earth. Strange. Very, very strange. When you look at Proxima Centauri, that's about 4.24 light years away, 4.25 light years away. You're not seeing that star as it is now. You're seeing it as it was 4.25 years ago. And normally this is where I love to be in a lecture hall, because now we can really start playing with some mind-bending ideas. Because it is impossible for me to observe the present. I can only observe things as they were, even if it's just nanoseconds. So usually the lecture hall that I work in is about 10 nanolight seconds across. But that means it would take light about 10 nanoseconds to travel all the way across it. Very, very, very short amount of time. But that's not really the point I'm trying to make right here. It's just, if I were to look out at you sitting in my lecture hall, something that I dearly wish we could do, what would I actually be observing? The light would be coming down, reflecting off of all of your lovely faces, and then coming to my eyes. And I would see you. Except that light would have taken some time to reflect off of your face and then reach my eyes. I wouldn't be seeing you as you are in now. I'd be seeing you as you were billionths of a second ago. And the further you are away from me, the more into the past, the more disconnected from now I am. Such that the people that are sitting closer to me, I'm actually seeing them closer to my present than the people in the people in the back of the room. That's just crazy. That's weird. It's almost as if time and space are somehow connected to one another. Some sort of weird space-time. So, light. Absolutely fascinating to consider. It has a finite speed limit. We've already discovered one of its properties, and we've had a lot of fun playing with that idea. I want to explore that idea a little bit more and share with you this video. This demonstrates the speed of light. Let's see here. So the speed of light, it could orbit the Earth 7.5 times every second. It gets to the moon and back. Well, the travel time to the moon is 1.255 seconds. And this is a real-time simulator. So this beam of light would be traveling at light speed, scaled accordingly. And now you're watching light as it's trying to make its way to Mars, which is 3 light minutes away. I know these are blinking kind of fast. You could do the sun. The Earth is a little over 8 light minutes away. And then you have Mercury, at about 3 light minutes away from the sun, Venus at about 5 or 6 light minutes away from the sun. And this is light leaving the sun, going out into the universe. This is just in our solar system. And all of a sudden, that really, 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 really incredibly fast, the fastest thing that can exist in the universe, light, seems really slow. So hopefully this really hammers into it. It gives you another scaling thing to realize just how enormous the universe is. Even within our solar system, the speed of light seems slow. Across the scales of the universe, though, it is incredibly slow. Now, I know that video blinked by pretty quickly, so there is the full video. These are done by Dr. James Donahue, who used to work for NASA, and he has this very, very, very long film where you could watch it in the background while you study for exam 1, where it is a real-time simulation of light leaving the sun, going all the way to Pluto, which has a distance of 5 light hours and 28 minutes. So notice that this video is 5 hours and 28 minutes long, and you can watch a beam of light, a photon leaving the sun, as it makes its way across the solar system. Nobody wants to sit around for 5 hours, but I wanted to go ahead and show this to you. I'll put links in the week 6 README so you can access these videos if you want to. Right. Which brings us to, what the heck is light? This thing that travels at the speed of light, no matter what kind of light it is. What is Dr. Lindsay talking about whenever he says different types of light? What kinds of light? Isn't light just light? So let's get to what the very nature of light is. And I'm just going to blast you a little bit up front with technically what light is. Light is electromagnetic radiation. So let's break that term down. Electromagnetic. Electro means relating to an electric field. Magnetic means relating to a magnetic field. So over here, I just have a picture of a magnetic field created by a magnet, where these would be the magnetic field lines of force. We could do the same sorts of things for gravity, but you can't create a dipole like this. But here would be a drawing of a magnetic field. Here is a drawing of an electric field, where instead of a magnet, you have a positive charge and a negative charge. Pretty much the same in the structure. And in fact, electricity and magnetism are 2 parts of the same force, the 2 sides of the same coin. They are working together with one another. One gives rise to the other, and the other gives rise to the other. They're connected into a single force called the electromagnetic force, or electromagnetism. And electromagnetism is one of the 4 fundamental forces of nature. We've already talked about one of the 4, gravity. Second one is electromagnetism. Slightly different than gravity, because gravity only worked one way, it pulled things together. Electromagnetism can pull things together or repel them. So it can be attractive or repulsive. 2 like charges, 2 positive charges will push away from one another. 2 negative charges will push away from one another. A positive and a negative charge will pull towards one another. A north pole and north pole of a magnet will push away from one another. South pole and south pole will push away from one another. A north and a south pole will get pulled together. So we're not going to really go into the details of really understanding what an electric field is, or a magnetic field, or anything about field theory. I just wanted to tell you all of this so that you know that electromagnetism is one of the 4 fundamental forces. And it, at the very nature, is light. Light is the carrier of this force. It is the fundamental particle, it is the fundamental thing that carries the electromagnetic force, transports it from one place in the universe to another place in the universe. I know, it gets really, really strange. What are the other 2 fundamental forces of nature? We're not going to really mention these in this class, but you have the weak nuclear force and the strong nuclear force are the other fundamental forces of nature. Okay, so light is something to do with electromagnetism, electric and magnetic fields. Light is also radiation, electromagnetic radiation. What is radiation? Well, radiation is just a fancy physics term to say it's any way that we can take energy from one place and put it through another place through space. without necessarily having to connect those two things together. So it is just a way to send energy from one place to another place. This is usually done in the form of waves or particles. So examples would be electromagnetic radiation. So send energy by an electromagnetic wave. Particle radiation, shoot some protons at somebody, because that's what we do whenever we're bored, is we shoot protons at one another. Okay, maybe not. Actually, don't bombard somebody with protons. Nobody needs that kind of radiation in their lives. Acoustic radiation, so if you're listening to this with the sound up, you can hear my voice. You are hearing acoustic radiation, sound, and gravitational radiation. Those are just a couple of examples. So just various types of radiation. It's much more than what you probably think about when you hear radiation. You think, don't go near that uranium, because that uranium is giving off radiation. And if you go too near to it, that radiation will do something to you and then you'll die. Nobody would be very happy if I were to have a giant hunk of uranium and then tell you to come gather around and take a look at it. Uranium gives off particle radiation, and that's what would be causing the damage to you if you got too close to uranium, especially uranium-235. Okay, let's put all that together. So radiation is just a way to transport energy. You can think about it as a way that you can transport information, which is what we're after, information about the universe. It's taking something in energy and putting it somewhere else in the universe, carrying that information with it. So it's also an electromagnetic field. It's electromagnetic. So light is the transfer of electromagnetic energy through space. It's also what we see. Why is some light red light though, and some light is sort of white in color? What's the difference? And for that, we really do have to look at the electromagnetic nature of light. In fact, we have to look at light as an electromagnetic wave. Other parts of this, to understand light, we're going to have to look at light not as a wave, but as a particle, because light is a wave and a particle simultaneously, which doesn't make sense. I know that. I will freely admit it. People that don't admit that that doesn't make sense, they are lying to you. It's weird. Light is both a wave and a particle simultaneously. A wave is like ripples on a pond. The ripples are everywhere on the pond. A particle is a thing in a distinct location. So a wave is dispersed over a large volume, a large region of space. A particle is in a very distinct location in space. But light is both at the same time. As a wave, light has all the properties of waves. As a particle, and a particle of light, that's what we call a photon, a word you've probably heard before. What the value of that part, and one of the more powerful things we can do is, as a photon, as a distinct particle, we can look at light as carrying a very specific energy. So this is this wave particle duality, as we call it, that is both a wave and a particle simultaneously, and it's constantly exhibiting properties of both, means that light carries a whole lot of information, despite it being really, 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 really weird. And what's even stranger is you can design experiments to make light go from looking like a wave to looking like a particle, simply by having a camera there. There's the famous double slit experiment where you shoot one photon at a time through just a board that has these two little slits through it. As a particle, if you send out one photon at a time, as a particle, it would have to go through either the top slit or the bottom slit. If you know if it goes through the top slit or bottom slit, then it should just basically, like you're throwing balls through little slots. You should get a pattern where it hits either, if it went through the top, it hit the top part. If it went through the bottom, it hit at the bottom part. As a wave, light could just go through both the top and the bottom parts, just like if you had a bay and you had two inlets to the bay, a water wave would go through and then spread out through the bay. So you'd expect a pattern, a different kind of pattern if you're observing that. And I know I'm getting into a little bit strange things here, but in one case, you could observe light as a wave. In another case, you could observe light as a particle. And what's strange is if you don't actually monitor which slit the light went through, the photon went through, you will see light as a wave. It'll make a wave pattern on your detector. However, if you just put a little tiny thing that can tell you it went through either the top slit or the bottom slit, all of a sudden the results of your experiments, they change. And you don't get a wave pattern, you get a ballistic pattern of shooting photons through discrete slots. You change the outcome of the experiment just by observing it. Light is weird. This wave particle duality is weird. Definitely, we're not going to go into that level in this class, but it is so fascinating that I had to share it with you. And I just want to go ahead and let you know that in this class, since light is electromagnetic radiation, and we're mostly going to be talking about electromagnetic waves, light as a wave, you can use these terms interchangeably. Light, electromagnetic radiation, and electromagnetic wave. So anytime you see any of those terms, you're really just talking about the same thing, what we just commonly call light. Also, electromagnetic radiation is not fun to type out over and over and over and over and over again. So often it's just abbreviated EM for the electric part and the magnetic part. So you might see things say EM wave or EM radiation. That's electromagnetic. Now I want to end this video, this appreciation for how fascinating and weird light is, with why we're going to be spending so much time studying it. Hopefully I've motivated that already, but really if we can just understand the nature of light, then we really can start prying out the secrets of the universe. If we know why light is doing what it does, if we can understand light as a wave and all the properties that entails, if we can understand light as a particle and everything that entails as well, then we can use all of that information, that understanding of nature, to really, really get at what's happening. And I want to just walk you through a little bit of this. This is sort of a quick little summary of a lot of the things we're going to hit. So let's look at the nature of light as a wave. How is light emitted, absorbed, and scattered? Where does light come from? What creates light? How do things, whenever light runs into something, how does it get absorbed? How does it bounce off? How is it scattered? This is really going to come down to a property of light as a wave, that the wavelength, how big the wave is physically measured, also equivalent to frequency of a light, and then what type of matter that light is interacting with, really controls whether light is emitted, absorbed, or scattered, which is really going to give us a method to determine the chemical composition and the chemical abundances, how much of each element things in the universe are made out of. That's going to be the entire second half of what we talk about, and that's going to be coming next week. If we're looking at dense objects, they emit light according to their temperatures. Very, very well-controlled way. So-called thermal radiation. And by understanding thermal radiation, all of a sudden we've come up with a method to determine the temperature of things in the universe. So we can use light to determine the temperature of objects. So what about the wave properties of light? Well, we have things like reflection, refraction, diffraction, interference, and the Doppler effect. We'll encounter each one of these in turns. Don't go scrambling trying to memorize all of these right now. I do have brief explanations in the notes, but we will really digest these when they become important to the class. But each one of these, how reflection works, how refraction works, how diffraction works, how interference of light works, and how the Doppler effects works, each one of these can be exploited by the understanding how they work. We then gain the knowledge of that how whenever we observe something. So we can gain a lot of information. We can also, if we understand how reflection and refraction work and diffraction, we can build really advanced light detection and light control instruments so we can study light at fine detail. So it allows us to develop technologies, and it's also giving us information. And I didn't have a bullet here for light as a particle. Light as a particle, the key is going to come down to considering a photon, is that every particle of light carries a very, very specific energy. And it comes down to a single property of that photon, of what determines that energy. And that's going to be the wavelength of that light. And then that wavelength of that light determines how that light is going to interact with things like matter in the universe. I know, that's all a lot coming at you at once. We're going to slowly pick this apart all the way through Unit 1, Part 4. Because each time that we understand a little bit more about light, we're going to get a new window of understanding into the universe. We will be able to take our cosmic messenger, light, and determine some fundamental things about the universe. And we will understand, or have a better understanding, of how astronomers know so much about this universe that we live in. All right, so this was very much a lot of information just to motivate you about light. I will see you as we start to go into the details about light. So I will see you in this week's video.